Okay, so welcome to today's colloquium. It will be given by our great guy, Steve Butler. He will be speaking about aspects of normalized Laplacian, and if he is fast enough, he will show us some juggling at the end. Maybe. So.
Well, Bernard said he was going to talk about how it's great to have me back, and I was going to start with, it's great to be here, it's wonderful. I hear so many wonderful things about Iowa State. So I'm going to talk about what I do. This is a lot of what I like to do with my research. I've had several very good graduate students who've also worked on this. I'll mention some progress. Now, in case you get sidetracked or you get lost, here's something to think about. So there's this curious set of numbers. It's a multiset, so take the numbers 2, -1, and -1. And you do some basic, elementary school arithmetic, where you form an addition table and you form a multiplication table. So if you do that, you get the numbers here, and 4, 1, 1, and so forth and so on. Multiplication table, you get the numbers there. Now, the very curious thing about these two tables is that if you just look at the actual numbers here, they're the exact same numbers. They're slightly different rearrangement, but they're the same numbers. Now that's really interesting. It says that in terms of the sets, the set A plus A of all possible sums instead of A times A, instead of all possible products, are the same. Now, are there any other examples of this phenomenon? The answer is, of course, yeah, because you can do 0, 0, 0, 0, or 2, 2, 2, 2. Okay, all right. Are there any other non-trivial examples? Well, you can ponder that during the talk. And perhaps you can ponder, what does this have anything to do at all with the subject that he's talking about? Well, what am I talking about? So, here's the basic I had to explain my field in using only 3 words. This is what I would say. So graphs are these wonderful structures, and you can use graphs to model all sorts of very interesting things and interesting phenomenons. And one of the things you might want to do is you might want to somehow store a graph. So how can I store a graph? Well, I can store it by an array. I can index arrays. The rows and the columns are indexed by vertices, and then I put entries according to whether there's edges or not. So there's various rules. People said, well, an array, let's call it a matrix. And people say, matrix, sure, whatever. Matrix array doesn't really matter. But as soon as people said matrix, the linear algebra people were like, oh, this is good. Because matrices have some additional structure. Once we start thinking about a matrix and what it represents, we have lots of linear algebra tools. And one of the tools that we have are eigenvalues. Now, if I know the matrix, I know the graph, and vice versa. I can reconstruct it. If I know the matrix, I know the eigenvalues. However, I can't quite go the opposite way. So my area of mathematics basically says, how much can you say right here? If I know something about the eigenvalues, what can I conclude about the graph? Now, of course, usually we phrase in terms of matrices, but then we say, what is the graphical structure? What can we decide? So what can we say about a graph given the eigenvalues? Now, I'm not being as specific as I could be, because one thing is there's lots of matrices. So let me talk about a few of the very famous matrices. The most famous has to be the adjacency matrix. In this one, again, we're going to index everything by the vertices, so the rows are indexed by the vertices and the columns are indexed by the vertices. And the adjacency matrix is a 0 if there's no edge between those pair of vertices, and it's a 1 if there is an edge. Now, that's how we think about the adjacency matrix, but there's sort of a better way to think about the adjacency matrix. At first, it doesn't seem like the right way. Namely that the adjacency matrix is counting how many walks of length 1 there are between 2 vertices. And you're probably thinking, okay, that's true, but that's such a silly definition. Why would you ever do that? Well, the reason it's not so silly is if you raise the adjacency matrix to a power, it still counts walks. So if I take the adjacency matrix raised to the kth power, and I look at the entries, any entry gives me the number of walks between the 2 corresponding vertices. So the adjacency matrix is great for counting walks, and in particular, the eigenvalues can tell you about closed walks, and from that you can conclude all sorts of things. So for example, edges correspond to closed walks of length 2, so I can tell how many edges you have. I can tell whether or not a graph is bipartite, because there's a theorem that says a graph is bipartite if and only if there are no closed walks of odd length. So I can tell a lot of information about the graph by looking at the eigenvalues. Not everything, but some things. A popular matrix that people like is the Laplacian. It's very similar, except now instead of having just the adjacency, what we do is we have the D matrix, which is the diagonal matrix of degrees. And so the degree is how many edges are incident to a vertex. You take that matrix, subtract A. Now this is a very nice matrix. It's positive semi-definite. It's very easy to show that the row sums are 0, for instance, and so 0 is an eigenvalue. But in fact, you can go a little bit further. It turns out that the multiplicity of 0 is the number of connected components that your graph has. And so you can start saying things about how connected your graph is. And in particular, Laplacian has been used for various measures of connectivity. There's this notion of algebraic connectivity, which is tied to the Laplacian matrix. Because I know the sum of the degrees is twice the number of edges, I know that the trace is just the sum of the degrees. And so, therefore, I can conclude from the eigenvalues how many edges I have. Another thing that this Laplacian matrix does is there's a wonderful theorem called the matrix tree theorem, which says if I know the eigenvalues of the Laplacian, then I can tell you how many spanning trees the graph has. So we can get a lot of great information out of this matrix. Now, one of the recent trends in the last few decades, people are like, look, we need to be more optimistic, upbeat, more positive. And so recently people have said, well, look, let's just do the same thing for matrix theory. Let's make it the Steinless Laplacian. Now we add the adjacency matrix instead of subtracting the adjacency matrix. And you might say, okay, does that do anything? And it does. There are some subtle differences. It turns out, for instance, that now the multiplicity of 0 is not the number of components, it's the number of bipartite components. The reason that's true is if your graph is bipartite, then you get the same eigenvalues. It doesn't matter whether you add or subtract. If it's not bipartite, it does cause things to change. Again, we can tell how many edges we have.
Steve, what's a bipartite component?
A bipartite component is a component which is bipartite. No. So in a graph, you might have several parts where there's no edges in between these various parts. These are called the components. So now, if I blow this up, the component is bipartite. If I can split the vertices into two sets, U and V, such that the edges only go between U and V. So there's no edges in here, and there's no edges in there. So the idea of bipartite, two parts. So that's what that means, bipartite. Feel free to ask questions, by the way, as I go on. And in case you were hoping to see lots and lots of matrices, I do need to warn you, I haven't written down a single matrix in this slide. Well, that's not quite true. I do have one coming up. But this is about how we use the matrices. All right, let me talk to you about the real matrix. This is the matrix, the most important matrix. Depending on who you ask. But for me, this is the one. The normalized Laplacian, this is the one we're going to talk about. Now, how is it defined? Well, usually, when people are being very lazy, they define it this way. It's pretty good. It says you take your adjacency matrix, and you multiply on the left and the right by d to the minus 1/2 power. Now, the reason I say this, there's a little bit of subtlety whenever you have an isolated vertex where you have degree 0, because then you have something in the form 0 to the minus 1/2. As long as you ignore those graphs, this definition is right. And it turns out you can ignore those graphs. So don't worry too much. You can take this as a definition. Now you might say, well, okay, are you going to talk about the normalized adjacency and the normalized Steinless Laplacian? And the answer is no. It doesn't really matter which one we normalize. Once you normalize one, you really have normalized all of them. So I could talk about the normalized adjacency, but any results will be equivalent to anything you get for the normalized Laplacian. So you might say, well, why did you normalize the Laplacian? Good question. Because my advisor did it, and I must do everything that she did, because it's the tradition. It's you follow in the footsteps of your advisor, and she came up with some really good stuff. I will say that I've heard some people jokingly call this the San Diego Laplacian, just because everybody who works on this matrix is connected to UC San Diego. Now, why would we want this matrix? Well, first thing is, a lot of combinatorial people, they get a little bit nervous about this because you have these square roots, but we'll handle those later. But the real reason why we want this is because this is really getting back to random walks. And random walks are very nice. You can learn a lot of information about a graph by knowing something about how random walks are behaving. In particular, how quickly do they converge, how quickly does a process diffuse on a graph. And the information from these eigenvalues gives you the information about what's going on. Now there's some nice things. Because of the normalization, all eigenvalues lie in between the interval from 0 to 2. So that sort of helps to compare graphs of different sizes and different orders. That's philosophical. I'll avoid doing that. The multiplicity of 0 is the number of components. The multiplicity of 2 is the number of bipartite components. I can test for bipartiteness, now looking for symmetry. But you have to have a trade-off. And the trade-off is you can't always detect the number of edges. And I found that very fascinating. And it's sort of somehow counterintuitive, because when you're a combinatorial person, you like to combinatorialate, which is another way of saying you like to count. You know, and it's like, well, you can't even count the most basic thing about a graph. Why would this be useful for somebody in combinatorics? There's trade-offs, but anyways. So let's summarize what we have here. This is my one matrix that I'm going to show you, just so you can see that what do we have? Well, we have the four matrices: the adjacency, Laplacian, silence Laplacian, normalized Laplacian. Then we have these four properties. Is it bipartite? How many components? How many components are bipartite? How many edges are there? And you'll see I've put yeses and nos. Yeses are if I know just the eigenvalues and nothing else, I can determine the answer to these four things. No says you cannot determine that, in that there are graphs which have the same eigenvalues, but have different structure. Now, one important thing is that no one matrix is clearly the best. It depends partly on what your application is as to what matrix you should use. So, a lot of the art of spectral graph theory is deciding what matrix should you be working with. Now, most people, when they prove results, they do things first for regular graphs. Regular graphs are very, very nice. But it turns out, for regular graphs, it doesn't matter which of these you use. Because once a graph is regular, if you have the eigenvalues for one, you have the eigenvalues for the rest. They correspond to simple shifts or translations or scaling. So there's really no subtlety with regular graphs. You get everything at once. When it's not regular, that's when things get more subtle, and that's when a lot of people struggle. So how do we handle that? Now the other important thing is, because as anybody in algebra knows, notice that this is symmetrical, which indicates there's something real about what's going on here. So that's my one linear algebra joke. So okay, apparently not even my students in linear algebra laughed at that one. Okay. Let me just point out what I mean by no's. These are graphs for the various matrices, and for each matrix I've drawn one pair of graphs. These pairs of graphs have the same eigenvalues for a particular matrix. So in other words, these two graphs are cospectral for the Laplacian matrix. This one has a triangle, and if you have a triangle, there's no way you can be bipartite. This one you can split into two parts, so it is bipartite. So here is an example of what I mentioned earlier, where it says I can have two graphs which are cospectral but have different number of edges. And the classic example is if you just take complete bipartite graphs, because complete bipartite graphs always have the same spectrum. They have an eigenvalue of 0, they have an eigenvalue of 2, and all the other eigenvalues are 1, regardless of how you split the two sizes of the two parts. So here, I have a K22 is what we call it. There's two vertices in one part, two vertices in another part, all edges in between. Here this is K13, one vertex in one part, 3 in the other part, all edges in between. And this is the classic example, but the other thing is, until about maybe 3 or 4 years ago, this was pretty much the only example. It was known that things could happen, but nobody knew how to actually make these graphs. We've made a lot of progress on that. We have lots of ways to construct graphs which have different number of edges, and I'll show you a few of them. These are some things that I found in the last several years. So let me answer a question: why do we want to normalize? Well, normalizing can be very good for us. So I'm going to start with a very basic theorem from linear algebra, which says if I have any matrix and I look at x star by, that's at most the largest singular value of the matrix times the norm of x and the norm of y. Now, this is not what I'm going to prove. I'm just going to inherit this from linear algebra. My goal is to show you I can use tools from linear algebra to prove things which are interesting about graphs. Now, something completely different looking is I'm going to define this notion of discrepancy. Discrepancy is a measurement of just sort of how far off from random my edges are. So in particular, I'm interested in comparing how many edges I have between pairs of vertices. So E of x, y says the following. I have my graph, and I take two chunks, x and y, subsets, and I look at how many edges are actually there. So the number of edges present, that's what I'm calling E of x, y. If my graph is deregulated, I can say, well, how many would I expect if everything were perfectly random? And the answer is I would expect roughly d over n possible fraction of the number. So the size of x times the size of y is the number of possible edges between the two sets. And then I would expect this fraction of them to be present. So that's how many I have versus how many I expect. So I want these to be very small if my graph was very random-like. So I want to see, can I bound it to be very small? And so we're going to say alpha is this alpha, the smallest you can make that is called the discrepancy. And so our goal is, can we say anything about this alpha? If alpha is small, my graph is random. If alpha is large, my graph is not random. Well, here we go. So this is a theorem attributed to Alon and Chung, and probably done by several people, which says that discrepancy is bounded by the second largest singular value of your adjacency matrix. Now, why? Here's the whole proof. We basically just take this theorem, and we just choose some nice matrices. The vector x is what we call the indicator vector. It's 1 if we are a vertex in x, 0 otherwise. The vector y is the same thing for the set y. And then here's your matrix. You take A minus d over n times j. Now this minus d over n times j is pulling out your largest eigenvalue and zeroing it. And now you do nothing other than you just multiply that up here. The left-hand side, you work it out, becomes this ratio, or sorry, this expression. The right-hand side, this becomes sigma b. I've pulled out my largest singular value, so it's my second largest singular value. The norm of x, norm of y is how many ones you have. It's the size of x, the size of y, square root. So once you have linear algebra, you can prove some very nice, simple things. Now that's just adjacency matrix.
What is the d in the d regular?
D is, okay, so d regular talks about degrees. So whenever we say d regular, that means that if I look at every single vertex, or rather any vertex at all, how many edges does it have connected to it? And it's, the number of edges is d. Or if you like, if you're a vertex, how many neighbors do you have? You have d neighbors. So there's somehow sort of a notion of locally you look the same. So you don't have any vertices which are connected to many things.
Every vertex has the same number of edges?
Every vertex has the same number of edges. Okay, so this is great, but one small thing is that you have to assume that you have this nice structure. You have this deregularity. Well, are all graphs deregular? And the answer is, of course, no. All graphs are not deregular. There are many graphs which are not. One famous example is the internet graph. I can think of every site on the internet as a vertex, and I can think of links as these edges. Now, I happen to find two sites at random. One of these is www.funnycatpics.com. It is very funny because they use an X here. And the other one is www.google.com. And these are two very important websites. One of them is a major driver of internet traffic, and the other one is a search engine. But certainly, most people would say, you know, these sites aren't really comparable. But what makes them different? What makes them different is really how I think about things. Well, really, the thing is lots and lots of people connect to Google, or Google connects to them. So there's lots of connections with Google, not so many with Funny Cat Pics. So I need to change my interpretation of how do I think of what's important for size. And so when I looked previously, I talked about the size of x. It's how many vertices were in x. That's the vertex-centric viewpoint, whereas the number of vertices that's important. I want to change that. It's not the number of vertices that's important. It's how many edges are that you have. So it's the number of edges that make you important or not important. So we change, instead of saying size of x, we have this new notion of volume of x. And the volume is the sum of the degrees. It's how many edges you have that you're connected to. So I can define discrepancy in a very similar way, but unfortunately to fit on one slide, I just jumped to the result, which says, if I have a graph, and I have any set of vertices, I can do the same thing. I can say, how many edges do I have? That doesn't change. But now I have a new way to express how many edges I should expect. So this volume x, volume y, depending upon how many edges are present in x and y, will tell me how many edges I should expect between the two of them. So again, I can compare the difference between the expected versus actual, and I can bound it by this small term, square root of volume x, volume y. This is the normalized adjacency matrix, but as I've already mentioned, normalized adjacency matrix is the same as the normalized Laplacian matrix up to a very easy shift. How do you prove it? The proof is the exact same. You just choose vectors x, y, and b a little more carefully. There's not a lot to the proof. I will say one of my first results, I was very proud of this. So my advisor is Fan Chung. She had me work on this problem and said, okay, so we know if your discrepancy, if your singular value is small, that says your discrepancy is small, that says you have a good graph. If you have a good graph, must your singular value be small? And the answer is yes, and that takes a lot of work, but I did that. I'm really happy with that result, but I'm not going to do that because I want to talk about more recent things. Okay, but the moral is, normalizing is good. We can get a lot of nice things from normalizing. So now I'm going to shift gears. So that result is more of an analytical result. I want to switch more to algebraic. I really want to understand the structure of what's going on. And this is some of the things I've been working on in the last 2 or 3 years. One of the things is I want to move away from thinking about graphs as binary, 0, 1, edge or not edge. I want to move to thinking of graphs as weighted. So between any pair of vertices, I have an edge and it has a weight attached to it. If you like, you can think of it as I have a graph and edges can have multiple copies, so it's sort of a multigraph. And then the weight is the number of edges between pairs of vertices. But once you have this notion of a weighted edge, you can talk about the degrees. It's the sum of the incident weights. You can define your adjacency now as the weights of the vertices, so the weights between vertices. You can define your degree matrix as the degrees now. And then you can still define the Laplacian as before. Well, now we can talk about the normalized Laplacian for weighted graphs, and implicitly I'm going to have this in the background. We'll see it's a very useful thing to start thinking about weighted graphs. Well, every talk, of course, should have one joke and one proof. They should not be the same. Now, here we go. Here's my proof. My claim is if I have any graph, and then I just scale all the weights by the same amount. So now all my weights currently are weight 2. I scale it, so now they're all weight 6. That those graphs are cospectral. But more than that, they're not just cospectral, they're above that, they're beyond that. They're co-normalized Laplacian, which is, they're co-matrix. I don't know if there's a real term for this. So in other words, this normalization, you lose any effect from scaling. So the normalized Laplacian for the graph G is the same as the normalized Laplacian for the graph alpha times G. And here's the proof. You just say, well, what's the effect of alpha? Well, it scales this part by alpha. It scales this part by alpha to the minus a half. And it scales that part by alpha to the minus 1/2, and then if you just do your math, they all cancel. So it works. Now this is such a simple and obvious thing, it can't possibly be useful. Except it is, and we'll show you in a few minutes.
Before you go on, do the weights have to be positive?
We tend to assume they're positive. But you can use, I have done examples of things where you have negative weights.
So yeah, that's not a problem for this result.
Not for this result. Generally speaking, most graphs have positive weights, but there have been cases where I've used negative weights for normalized Laplacian. I try not to tell too many people I do that.
Directed graphs could have negative weights, right?
Well, any graph can have a negative weight. You just have to come up with a good story. As long as you've got a good story, yeah, go ahead, make your weights negative. So, yeah, my weights are positive. Everything that I'm going to do, I'm going to do construction, so I don't run into that obstacle. Okay, the other thing that's good to know is the notion of harmonic eigenvector. So I should start with just eigenvectors for the adjacency matrix. There's a nice way to think about an eigenvector for the adjacency matrix. Now what do we mean? We mean if I multiply my matrix A times Y, I end up with a scaled version of y. But the way I can think about it is it's literally doing a local operation. So a times y says at every vertex do the following operation. I sum all the weights between my current vertex t and the neighbors times what is the value of the function at the neighbors. That should be equal to this mu times y at the vertex. I haven't done anything more sophisticated than saying what's the tth entry on each side. It looks like I've done something, but I haven't. So that's the adjacency matrix. Now, what happens for the normalized Laplacian? Normalized Laplacian, well, we have this expression, but one of the things I mentioned, those square roots of d, always pesky. We want to try to find a way to get rid of those. So we can say, look, don't think of the vectors as your important things. Let's scale them. So we scale them by this factor d to the 1/2. And we call this vector y the harmonic eigenvector. Now, why do we care about this? Well, if I start with this expression, then once I replace x by d to the 1/2 times y, I get something pretty simple. D minus a times y equals lambda y. Or I just rearrange. A times y is 1 minus lambda d times y. Or I just do the same thing I did up here, and I say, what does that mean? Well, I still have this adjacency operation going on. So I still have this nice operation on the left. What happens to the right? The only real big thing, because I can think about changing mu to 1 minus lambda, the only real big thing is this extra factor right here, the degree. The degree doesn't show up here. So normalization, the normalized Laplacian, that's the effect. So if you like working with things which are much nicer, you work with harmonic eigenvectors. One thing you get from this automatically, by the way, is if I have something which is an eigenvalue of 0 for the adjacency matrix, it's a harmonic eigenvector for the eigenvalue 1. Because 1 minus lambda equals 0. I get 0 on this side, it was 0 on that side. So there's this nice correspondence that you have going on there. Okay, which is what I said right there. All right. Now, let me talk a little bit about graph operations. There's a couple things you might want to do with the graph, which is you have two graphs, you build up a bigger graph. In the interest of time, I will just say we can do various things. The Cartesian product says you take the graph, you do a Cartesian product of the vertices, more or less, well, maybe it's easier to draw a picture of what's going on. Here's some pictures. So if I want to take the Cartesian product of K22, that's the same as a 4 cycle down here with K2. I basically put 2 copies, then I put all edges in between. So I do the same thing here, all edges in between. There's a strong product, and there's what's called the join. The join is a very nice operation. For the join, you take a graph. This is what we call K2. It's a complete graph on 2 edges. And K22 is this cycle, and I put in all possible edges. Now, the punchline of all of this is that these are really nice operations for spectral graph theory. In particular, if you work for the adjacency matrix, once I know the eigenvalues of my 2 graphs, and I do a Cartesian product, I get the sum of the eigenvalues. If I do a strong product, I get a sort of a crazy expression. And then similarly, you get a nice expression for the joins. However, all those nice formulas that we had, they work terrible for the normalized Laplacian in that you cannot build off these graphs in a nice way. So there's no nice way to know the eigenvalues for the Cartesian product or the strong product just by knowing the eigenvalues of your original graph. And the proof is you just do some examples and you say, well, look, K22 and K13, those are the 2 graphs I said at the very beginning are cospectral. They have the same eigenvalues. These are K2, that's the same graph. So if I could tell the eigenvalues, then I could determine the eigenvalues for these graphs, and they have to be the same, but they're not. So there's a lot of limitations. So there's a lot of things that we used to be able to do that we can't do. Now, one nice product that we can actually say something about is the Kronecker product. And, oh wait, whoops, did I go backwards? Ah, yeah. One nice product that we can say something about is the Kronecker product. And the way that works is if I have a graph on 2 vertices and a graph on 2 vertices and I take the product, I will produce this graph. In particular, I say 2 pairs of vertices in my new graph are adjacent if and only if okay, well, I should write this down. UV is adjacent to WX if and only if U is adjacent to W and B is adjacent to X. That's the Kronecker product. It comes from Kronecker product of matrices. So we can find the eigenvalues of that one. They're very, very nice. Just as a side note, of course, regular graphs are always very nice because it doesn't matter what matrix you're using. So if you want to know the eigenvalues for the Cartesian product or the strong product of regular graphs, you just shift everything into a different spectrum, do the operation where you know the eigenvalues, shift everything back. For graphs which are doing the join, you can take the join of two graphs which are regular, and you get a nice expression, more or less. You may disagree with me on how nice this expression is, but I can do the join operation. Now the join operation is pictorially very pretty. It says you start with one graph G, you start with a different graph H, and then you put in all possible edges in between join and H. Between G and H. That's the join. So that's what we can do. We can determine it when the graphs are regular. And there's a great philosophy here that comes into play, which is a wonderful idea. Unfortunately, looking at my time here, I don't know if I can go into too much detail, but I'll still go into too much detail. Anyways. And the nice philosophy is the following. It says that I really know something about regular graphs. So if I have a part up here, so I'm thinking of my graph as being in two parts. So there's one part up here where I have this piece up here, and this is a regular subgraph. Now what I mean here is if I just restricted myself to just that part of the graph and I said, what do I have? That graph would be regular. Or in other words, the induced version on the induced graph on those vertices is regular. This down here can be whatever it wants. This is arbitrary. But the only other thing is how are they connected? And the moral is there's some set of vertices here, and every vertex upstairs connects with every vertex downstairs. So there's sort of a nice gluing going on. If you have that, then there's something beautiful that happens. Namely, I can take an eigenvector for this graph by itself, and I can extend it to the larger version of the graph. So in other words, adding this part in, I can still get the same eigenvector being used. But it shifts the eigenvalues. That's what's going on with these things here, is shifting these eigenvalues. Now, when you have a graph which is a join, what's happening is you have a regular part up here, and you have a regular part down here. And you can say, well, these things are connected. So that's where you get most of the eigenvalues from. Now, I did tell you one small lie, that you can get the eigenvectors lift up. There is one eigenvector which does not lift up naturally, which is the trivial eigenvector. Why do people love regular graphs? And the answer is they love regular graphs in spectral graph theory for one reason and one reason only. And that is because they know a single eigenvector. That is why they love regular graphs. Don't let anybody tell you different. So we still have that one really trivial eigenvector, except that we call it a harmonic eigenvector, which is the all ones. That one can't extend naturally. But once I've extended the rest, what's true is I can collapse. So I come here, I get lots of eigenvectors here, I get lots of eigenvectors here. That gives me this part, gives me that part. How do I find the rest? Well, the moral is I collapse everything down. I collapse this down to a single vertex. I collapse this down to a single vertex. I have one really big edge here, one edge up here, one edge up here. These are weighted according to, depending upon what happened with these graphs, how many edges were there, what were the degrees. But now I've gotten down to a graph which is small. So small, it's on two vertices, I can actually do graphs on two vertices explicitly, and that's how I find the remaining two eigenvalues. So there's this nice collapsing idea that goes on here. So that's available to me. Now, that's very general. Let me go through a really easy, specific case after Ryan asked me a question.
I have a question about what it means to cone. So you say
Cone.
between the regular subgraph
Right.
and the other graph it's complete. Does that mean there are no other edges between the regular subgraph and the rest of the graph, or could there be others?
No, all the graph, yeah, so there's only these edges and none others.
I understand.
Down here, these are arbitrary. I don't care what they do. Well, I mean, I care, but not for the theory. I don't know if calling it's a technical definition or not, but I use it often enough that people don't usually question me. You just speak with authority, nobody doubts you. So I'm going to do one really easy special case to help put this into context, to help you see what's going on. And that's when we have twin vertices. So twin vertices are really nice. Basically, it says I have two vertices, and they have the same sets of neighbors. There's a little bit more technical definition once you get into weighted graphs, but that's how you should think of it. Vertices which have the same set of neighbors. So U and V, they both have the same pair of neighbors, but W has a different set of neighbors than those two. So W is not a twin of U and V. Good. Now, what can we do with twins? Well, the point is, these two vertices here correspond to this part up here. And I want to show what goes on. Now, one thing that's really good about these are, I know, a nice eigenvector. Namely, the eigenvector which assigns 1 to one of the vertices and -1 to the other. If I come back here, in other words, there's a vertex, I put 1 at this vertex, I put -1 at that vertex, I put 0 at every other vertex. Now what happens is if I'm down here, I'll have a 1 there, and a -1 there, their sum is 0. If I'm up here, well, all the neighbors are 0. If I'm over here, I'm really far away from anything that happens interesting, so I still get all the sums are 0. So this nice this nice relationship gives me a nice eigenvector, which gives me an eigenvalue of 1. Now, every other eigenvector has to be perpendicular to these two. So I like to think of the notion of what I call an uber vertex. Now, this was before uber became really popular. But what do I mean by an uber vertex? It's like a super vertex. Because now, every other eigenvector, it must be the case that they agree at U and V. So I don't need to think of these now as separate vertices. I'll think of them as one big vertex, and so I'm going to do that to my graph. I'm going to say, well, look, let's just collapse all those vertices down into one single vertex and see what I get. So once I have twins, I can do my collapsing. That's what was going on here. I was going to collapse down. So here's our philosophy. We look for twins. We know whenever we have a large group of twins, they're going to get lots of ones in the spectrum. And now, after I find all the ones, I have this big group which moves in unison. I move it to a single vertex. And to do that, I just need to add the weights when I put them all together into one single vertex. Now, after I've done that, I look at the graph that I have. And the graph that I have left, that gives me the other eigenvalues. Now, if it turns out that after I do this operation, I get two different graphs initially, and I reduce down to something where the two graphs are cospectral, then the original graphs were also cospectral. So let's give a very explicit example here. Here are two graphs, and on the left, there's these nice sets of twins right there. Actually triplets, but we call them twins still. And I'm just going to collapse these down on each case. And once I do that, I'm going to have 6 vertices left, and between any two vertices, I'm going to get 3, because I need to add up these weights. So 3, 3, 3, 3, 3, 3. On the right-hand side, I'm going to do this collapsing again. So I'm going to collapse these 6 different pairs. And if I do that, what will happen is I'll end up with 6 vertices. And in each vertex, between any pairs, there were 4 edges in between, so I get a nice cycle with edge weights 4. Now, 2 things to observe. Both graphs started with 12 vertices. And I pulled out 6 vertices. Each time I pulled out a vertex, I got an eigenvalue of 1. So there are 6 ones in the spectrum, plus the eigenvalues for these 2 parts. Now, the question is, can I say anything about the spectrum of these 2 things? Now, if I was very smart, I could say exactly what the spectrum was, but I don't even need to be that smart. What can I say about these graphs? Audience participation time. What's true about these 2 graphs?
They're cospectral.
But why are they cospectral?
Because they're multiples of each other.
Yeah, notice that I just scaled this one to get that one. That theorem which I said is so obvious it could never be useful. We're using it. In fact, these are going to have the exact same eigenvalues. It's the exact same matrix for the normalized Laplacian. So after I collapsed, I got down to the things that were cospectral. So that says that these 2 things were cospectral. Now the really tricky part. This has 18 edges. This has 24. Which means that you can have different number of edges. Now one of the things you should always do if you're proving things are not well, are cospectral, you actually have to say, are they the same graph or not? These are definitely not the same graph. You can generalize this really nicely. In other words, you can take this construction and go crazy by just start with any arbitrary bipartite graph you want. Doesn't matter, any one you want. Vertices of A and B. And you just have to choose some parameters to satisfy one thing. Namely, you have to choose your scaling factors. So S times A plus T times B is S prime times A plus T prime times B. And here's what you're going to do. You come to your graph, and every vertex in A, you blow it up to S independent vertices. Every vertex in B, you blow up to T independent vertices. And if there was an edge between those pairs of vertices originally, now you put in a complete bipartite graph. Do the same thing with S prime and T prime. The moral is the following. The number of vertices in your two new graphs are the exact same. That's what this one condition guarantees. Now, you collapse all your twins, because you basically are forming groups of twins. You collapse them back down. You get lots and lots of ones. But in each case, you get the same number of ones. And the resulting graphs are going to be the same. In fact, all that the resulting graphs are scaled versions of your original graph. And so you now have cospectral graphs. But if it's the case that ST and S prime T prime are not the same, they'll have different number of edges. So you can construct lots and lots of graphs with different number of edges where this is true. In some sense, complete bipartite graphs are a really super boring example where you start with the single graph on two vertices and an edge. That's your bipartite graph, and you blow up one side and blow up the other side. But we can do more interesting things. Here's another example. I didn't draw all the vertices. This A says that there are 8 vertices here, but if I drew 8 vertices there, you wouldn't be able to see them all. So trust me, there are 8 vertices here. There's 4 there, and so forth and so on, all the way around the circle. And the edge means a complete bipartite graph between the pairs. And if we do the same argument, you collapse, and you collapse there, then you get, again, 2 versions which differ by scaling. So, in other words, the construction I gave you on the previous slide is not the only option you have. There's lots of other options out there. But I will say there is a weakness in that this only works for bipartite graphs, and you might say, well, okay, bipartite graphs, they're kind of too nice. Is there anything else that works? Yeah, there's actually lots of examples for things which aren't bipartite. And at the same time we'll get that, we'll get something rather amazing. Because if you have different number of edges, it's possible that you can have a graph which is cospectral with a subgraph. In other words, I might have this graph right here, where k is arbitrary. You can choose k to be whatever you want. And this graph right here, and they will have the same eigenvalues, and the difference is these edges in between downstairs. So it's possible to be cospectral with a subgraph. Now, one of the interesting things is I said that this graph is related to random walks. So from a purely spectral point of view, these two random walks are indistinguishable. If all I know are the eigenvalues for the random walk, I cannot tell them apart. But somehow you feel like all these edges downstairs should matter. They should make a difference. But they don't. Okay. And I'll point out this is not bipartite because you have triangles. Now what do? We do the same thing that we've done before, where we have lots of twins. I've already grouped them very conveniently. So we collapse. And if we collapse, they collapse down to these two graphs here. And you might notice these are not just rescaled versions of one another. So what do I do now? Well, the good news is there are graphs on 5 vertices. That's small. And we can handle that. Or rather, I can say the computer can. We just check the characteristic polynomial, because the characteristic polynomial determines the eigenvalues. And it turns out the characteristic polynomial for both graphs is equal to this wonderful expression here. And so these two graphs are themselves cospectral. But those are the only interesting eigenvalues that remain after I collapse down. So the original graphs were cospectral. One thing I forgot to point out about this, this is a fun example. I like to point this out. If you choose k fairly large, this graph is a dense graph. It has order n squared over 4 edges. This graph is a sparse graph. It's just almost a tree. So you can have sparse graphs cospectral with dense supergraphs. It's very strange. Okay, all right, back to work. Let me mention, this is a preview for a talk to come, because this is not the talk I want to give you. I have a great student, she's in the audience, so I can say many great things about her, she won't be embarrassed. So I have a graduate student right now, and Kristen, who, well, up to the IMA last year, and I said, you know, Kristen, I found these great examples. And, you know, all these things happen, that all the proofs work the same way. You look at eigenvectors, you find the patterns, and just, you know, it all works out. And I said, you should go work on this. It'll take you 2 weeks. 6 months later, thanks to her perseverance, turns out I was wrong. I was as wrong as I could possibly be. We were able to find that there, in fact, there's this wonderful large family. I'll tell you roughly what I'm doing here. You have these little modules, cycles and paths, and you glue them together and you cycle around, and you code these by what you see here. So a path is a P, and a cycle is a C. So I can just read off the graph by the word P, P, C, C, P, 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 C. Here are C, C, P, P, C, 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 P. And so for every word in P and C, I have a graph. Now, what's the amazing thing is, Kristen and I were able to show, if you interchange P's and C's, the graphs you get are cospectral. And it can be true for any arbitrary word in P and C. And so these graphs are cospectral. But again, they have different number of edges. And you can get all sorts of really interesting examples coming out of this. This is just sort of scratching the surface. There's actually a lot more. But as I said, come back at the end of the semester. Kristen is going to give a fantastic talk about all of this. All right. Spoiler alerts, characteristic polynomials. All right, anyways. Last thing I want to mention, Kimmi's constant. So Kimmi's constant is this really interesting thing with random walks. And there's defined in a couple of different ways, and depending upon how you define it, the amazing thing is that it's in fact a constant. But here's one way I've heard it defined. It says, suppose you have a graph, you want to do a random walk. Well, you have a starting vertex, and you have a goal vertex. And what you're going to do is you're just going to move through the graph, and of course random walks might trace back over themselves, but eventually you get to this goal vertex. And once you hit your goal, you stop. Now, how long does it take you to get there? So in other words, what's the expected amount of time from where you start to where you end? It's called the first passage time. Well, you can figure that out for any pair of vertices. But now what if I tell you, I'm not going to tell you what your vertices are. I'm just going to say, look, you're going to randomly pick a start, you're randomly going to pick an end. What's the expected amount of time between that? That's Kimmi's constant. Now, it's known that if you have the eigenvalues of the transition matrix, D inverse times A, then this constant can be computed in terms of the spectrum. It's 1 over 1 minus rho I, except you throw out the trivial rho 0, which is 1. Now, why is this important to us? Well, D inverse A is really close to what we're doing. In fact, it turns out D inverse A is similar to the normalized adjacency matrix, which is a translation of the normalized Laplacian matrix. And when you write in terms of the normalized Laplacian matrix, this result becomes even nicer. It says the following: if you know what your eigenvalues of your normalized Laplacian are, then this constant is the sum of 1 over the eigenvalues, except for you throw out the eigenvalue 0. And that's the constant. But you can go even further, because you know it has this form that says, look, you go and write down the characteristic polynomial, then all you need to know are these last two coefficients. These last two coefficients are enough to give you Kimmi's constant. So you can use facts about the normalized Laplacian to compute Kimmi's constant for various classes of graphs. So one of the things you can do is if you have a graph with lots of structures, with lots of twins, you can collapse. You can get down to smaller graphs, and then you can use some various things like recursion. And I learned about this when I went up to visit Sean Fallett, who's at Regina, and I didn't really have a problem in mind when I went to visit, but within the first day we started talking about Kimmi's constant. It's like, okay, we're gonna find a good graph. Now, what would have a really high constant for Kimmi's constant? Intuition says you should take a very long path. that would have a very high constant. Because if you're at the very end of the path, it takes you a very long time to get from one end of the path to the other end of the path. Pretty good guess. Pretty good guess. That's roughly n squared over 6. And that was the best guess that Sean knew. Can you do better, or perhaps, depending on your perspective, worse? Is that as good as you can do? What do you think?
I know.
No, great answer. I love that answer. Because you know, of course, the answer is no. Otherwise, I wouldn't ask such a question. So you know the answer is no. But what can we do? And here's the construction. You split your vertices into 3 parts. You put a complete graph here, so all possible edges. You put a complete graph here, all possible edges. And then you put a long path of a third of the edges. So you split your edges into these 3 pieces. And it turns out that you can do it much better than n squared over 6. You can get all the way up to n cubed over 54. In fact, we have an explicit expression. Moreover, we actually are able to do it if I have p vertices here and q vertices there and r vertices there. We have an explicit expression for that, where we did it by figuring out the characteristic polynomial. Or rather, we found the last 2 coefficients. But we can't fit it on the slide. But this much we can fit on the slide, so that's why I'm doing this special case. So you can get Kimmi's constant very large. Okay, best possible? We don't know. Still a lot to do, lots of interesting things to say. Now, one of the things that's true, and I apologize, I know I'm in overtime, last minute and I'm done. You can't tell if a graph is regular with normalized Laplacian, which is very strange, because all other matrices you can. Now, because we can't tell if a graph is regular, lots of strange things happen. For example, you can have something be cospectral with a cycle. And there's infinitely many things where you have something cospectral with a cycle. Doesn't have to be bipartite, you can have that going on. So there's a lot of questions left, but the good news is I still have lots of graduate students who are willing to work with me. So, all right, I'll stop there. Thanks.
Okay, we are a little bit over time, so maybe if there are questions, let's do them offline and let's Steve think.
Okay.